Hello. In this video, I want to talk about the binomial theorem, and in particular, the binomial theorem when the exponent is a general real number. And I want to prove the result without using calculus. So let's remind ourselves what all that means. The simplest case of the binomial theorem generalizes this very familiar statement to powers here that are a natural number. So we can increase the power like this, and we can decrease it like that. And for me, natural numbers start at zero, so I'm going to include zero. So the numbers that appear here are, of course, Pascal's triangle, the binomial coefficients. This is 4 choose 2, for example. And that's all very familiar stuff. So we can write that slightly more formally, have a general real number and a general natural number. And we can write 1 plus x to the n as this sum, running from k of 0 to the n, of n choose k, x to the k. And we can write that out in this form. So this is just the formula for n choose k. This is the general term. And so those mean exactly the same thing. And when we advance to the exponent being a real number, this time we have a general real number as the power here. And it's very much the same, at least as far as the algebra is concerned, except that this series doesn't stop. So that's what we're going to prove. So let's go back to the natural number version, and let's rewrite this slightly. So I'm going to run the sum out to infinity. So in the case of the algebra version, that's fairly easy because when k gets beyond n, gets to n plus 1, this term is 0. This factor is 0, so this term is 0. And so are all the later terms because they all have this factor. So actually, this is the same as that. And so this is as well, the same as that. People get squeamish about having n choose k when k is bigger than n, but actually you shouldn't be. So how many ways are there of choosing 7 objects from a set of 3? Well, none. There aren't any. You can't do it. So of course it's 0. So of course that means the same as that. So now what we do is we define this function here to be that same thing, but with r now as a general real number. So starting with this version, that is exactly what we had before, and it's a straightforward function, isn't it? Nothing very complicated about it, except that it goes on forever. Now, writing it this version, now this no longer means the binomial coefficient. It no longer means r choose k. You can't choose 3 objects and 7.5 in any particular number of ways. That doesn't make sense. It's just another way of writing this. Except that it's a way of writing it that reminds us that if r happens to be a natural number, then this is that choosery thing. It is the binomial coefficient. So we know that r happens to be a natural number. This thing here is 1 plus x to the r, and our task is to prove that it is even if r is not a natural number. Now, this thing obviously is really a function of both x and r, isn't it? But I'm going to think of it as a function of r with x fixed. So far from doing any calculus on x, I'm actually going to fix x for the rest of the video. So we can imagine that x is some particular value. It's got to be less than 1 in absolute value. It might be 3/8 or whatever, and it's going to be fixed for the rest of the video. So if you want to prove it for another x, you'll have to go back to the beginning of the video and do it again. But anyway, so x is fixed, and we think of this as a function of r. The first thing to do, though, of course, is we have to prove that this means anything at all. In other words, that this infinite series does converge to something. Okay, so here's our infinite series. Let's consider the ratio of consecutive terms. So here it is. This denominator is this general term, and the numerator is the next term. So it's very similar. It's got one extra factor on the top of r minus k, one extra factor on the bottom of k plus 1, and one extra factor of x. So almost everything cancels, and we end up with this. And as k gets large, this tends to minus x, doesn't it? So if r is a sensible number, like 3.5 or minus 5 or something, then by the time k gets to 1,000,000, this is to all intents and purposes minus x. And that's the ratio of consecutive terms, and that ratio is less than 1 in absolute value. So it behaves exactly like a geometric sequence, and so it's going to converge. Now, there are several points in this video where I'm not strictly going to prove this thing to, as it were, university math standards, and this is one of them. So I'm expecting you to believe that it's plausible, at least, that if this series here, ends up looking pretty much exactly like a geometric sequence, then it's going to converge. The usual proof that you see of the binomial theorem actually uses Maclaurin's theorem. if you know what that is. If you don't, it doesn't really matter. It's a piece of relatively advanced calculus, and at least in English schools, it isn't introduced until way after this binomial theorem, and so you can't use that to prove it. And so I suspect it often isn't proved for A-level pupils. But actually, the Maclaurin's theorem is no let out for this sort of slight hand waviness, because the proof that Maclaurin's theorem works is actually a little bit subtle and is again sort of university level maths, although it's used in A level. Anyway, on we go. So we accept that this is converges. The other thing we have to accept is that it's going to converge to a continuous function. Now that's slightly subtler, but let me see how that works. So we see that the tail of this series behaves like a geometric series, and so we can chop the series in half quite far out to the right in such a way that the tail is absolutely tiny, like 10 to the minus 19 or something. And it's going to be tiny for all sort of nearby values of r, if you like. And what's before the tail is just a polynomial, so of course it's continuous. So the sum of those two things is continuous, because if you change r just a little bit, this is a polynomial, so it only changes a little bit, and the tail's so tiny anyway that doesn't change much either. So again, that's not a proper proof, but I hope you accept that that means that this thing, A, it converges something, and B, what it converges to is a continuous function of r. Okay, so let's think about what this function of r actually looks like. So we're going to multiply two versions of it together. So it's that times that. Now, there's a third point at which I'm going to play slightly fast and loose. I'm going to assume that we can work out what this is by multiplying it term by term, every one of these by every one of these, and adding them all up in any way we choose. So that again is a little bit of quite subtle maths to prove that that is valid. It is for a series like that. It's not valid for all series, but for one like this that converges rapidly with this sort of geometric series type ending, then it is valid. And by the way, it was Newton who first did all this stuff about binomial theorems with a non-natural number exponent, and he wouldn't have worried about any of this subtlety. So he would have been quite happy with all these things that we've assumed, because that level of sort of degree of rigor didn't really enter mathematics until quite some way after Newton. So we're just going to do the obvious thing here. And I suppose it would never occur to Newton that this isn't valid. So anyway, let's do that. So if we multiply any one of these by any one of these, we're going to get something with the power of x in it. And we're going to collect all the powers of x together. So constant terms, any one of those is that times that, and that's 1. The x is that times that plus that times that, so it's that. Quadratic terms a little bit more complicated, so it's 1 times that, and that times that. So let's collect all that together over 2 factorial. And what have we got here? So we've got r times r minus 1. We've got s times s minus 1. And what's left over is the cross term here, 2rs over 2 factorial. So that's just rs. Now that begins to look as though it might be equal to f of x of r plus x. After all, this is 1 plus r plus sx plus r plus s times r plus s minus 1 over 2 factorial x squared. Well, spoiler alert, it is that. Now, let's see if we can establish that. So let's look at the third term. So it's a little bit more complicated here. We have 1 times s choose 3, r times s choose 2, and so on. And again, I'm using this s choose 3 thing, not because it's actually s choose 3, but it's just a shorthand way of saying this. Okay, so we multiply it all out, put it over 3 factorial. This one here, for example, is s cubed minus 3s squared plus 2s. And all the rest works out. So these ones are only over 2 factorial, so we have to multiply them by 3. Collect all the terms by the power. So these are all the cubics, all the quadratics, and all the linear terms. And now look what happens here. So that is r plus s cubed, isn't it? R cubed plus 3r squared s plus 3rs squared plus s cubed. And this is minus 3 times r plus s squared. And this is 2r plus s. And lo and behold, compare that with this. So it's something cubed minus 3 times that thing squared plus 2 times that thing. So that's that. So that's what we wanted it to be. Great. So now let's look at the kth term. So let's look at the cubic term just again. That's what we just proved. We can write that this way. So that's r choose 0 times s choose 3 and so on. That's got to be r plus s choose 3. So the general term is going to look like that. We need to prove that. So we need to prove this, which is known as the Jules van der Monde identity. There's something funny about this. This guy here is a 13th, 14th century Chinese mathematician whose name is usually spelled ZHU, and so I presume it's pronounced Zhu. But this theorem always seems to be spelled CHU. I don't understand that. Anyway, that's who it is. And this is a French guy, much more recent. Right, so that's what we're trying to prove for K being a general natural number and R and S being real. Now then, the first thing to observe, this is easy if R and S happen to be natural numbers, because this is R plus S choose K. And if you're going to choose K things from a set of R plus a set of S, well, you've got to choose some R's and some S's. So you either choose no R's and all K S's, or one R and K minus one S's, or so on. So that's easy. That's definitely true if R and S are natural numbers. So now we consider this thing here, if we take that and subtract that from it. Now this is polynomial in R and S. So R and S are real variables. So it's a polynomial in the real variables R and S. And it's of degree at most K, because this is a degree K and that's a degree K. And it's zero whenever R and S are natural numbers, at least with R and S greater, R plus S being greater than or equal to K. Well, it sounds as though that jolly well ought to be zero, doesn't it? Just as the zero polynomial. And it is. So let's prove that. Of course, just that it's got a lot of zeros doesn't mean that it is zero. So polynomials for two variables usually have infinitely many roots, like this one. It's got all those roots. But the roots we have here are all these. So all the natural number points going on forever in both directions, a whole plane covered, the whole top right corner of the plane covered with roots. And we need to prove that that means that this thing is in fact zero. Okay. So we start with this polynomial. And the first thing we do is we form a new polynomial by adding k to all of the parameters. So if you like, that's shifting the graph of pk down and to the left, which means it's shifting all the roots down and to the left. So now it's still a polynomial of degree at most k, but it's now zero whenever R and S are natural numbers. Okay. And if you don't like the graph shifting idea, just look at if R and S are natural numbers, then these parameters are natural numbers whose sum is greater than K. So it's definitely right. Okay, right. So now we consider this thing. We set S equal to 0. And what we get then is a polynomial in R. Just it's ordinary, plain old-fashioned polynomial in R of degree less than or equal to K, but it's got infinitely many roots all along the x-axis, if you like, well, the R-axis. Well, that doesn't happen, does it? So that is actually 0, which means that this thing has no terms of the form just R to the A, because they're the ones that would survive if you set S equal to 0. And of course, in the same way, this has no terms in the form S to the anything. So all the terms are divisible by RS. So let's divide by RS. So we get a new polynomial dividing that one by RS. Now, this is a polynomial of degree at most K minus 2. And that's 0 whenever R and S, well, whenever R and S are positive integers anyway. We can't say anything about whether it's 0 when 0, because it's sort of nonsense anyway. So, but it's positive integers. But now we can play that translating trick again, move it down and to the left just one spot. And now it's a polynomial of degree K minus 2, which is 0 whenever R and S are natural numbers. I remind you of anything? Same here. So do it again. Round and round and round we go. And we end up with a polynomial of degree at most 1, which is 0 whenever R and S are natural numbers. Well, that's not going to happen, is it? That's definitely impossible. So now what have we done here? We've proved that when we've done all these transformations of P and ended up with the 0 polynomial. But what is that transformation? We've done a series of translations and of dividing by RS. So we can undo all those transformations and recover this from our original 0 polynomial by doing a succession of things which are either translations, up and to the right actually, or multiplying by RS. But none of those does anything to turn the 0 polynomial into anything else. So if you undo all those things, you've still got the 0 polynomial, which means this was 0 all along. So we've done it. Right. So actually, we've now proved that Joux van der Monde theorem, and we've now proved that we can take those question marks away. That really is true. So this times that is that. Well, now we've done all the hard work, really. So we've proved that, and we want to prove the sort of the extended version, where if we multiply any number of these fx's together, we end up with a single fx evaluated at the sum of all the parameters of this thing. Well, that's a simple inductive proof, isn't it? So suppose that one was true. Let's prove the next one along. So the product of n plus 1 of these things is the product of n of them times the last one. By the inductive hypothesis, that product is equal to that. And by the starting version, that times that is equal to that. So that's true. Right. Now then, what good is all that? We can now use it to work out what fx actually is. So let's suppose that m and n are co-prime positive integers, so no common factor. And we'll also assume that m is odd. So it's a third or 4/9 or whatever. Anyway, okay, so let's look at fx evaluated at this particular sort of rational number and raise it to the power m. Well, by that functional equation we've established, this is the product of m of these fx's. So it's a single fx evaluated at the sum of all these, which is m times that. So that's fx of n. And that's 1 plus x to the n, because we know what that is when n is a natural number. Hurrah. So now that means this must be the mth root of that, which is that. Hurrah. Now you see why we have to have n odd, because if n were even, we couldn't really quite deduce this. It would be sort of plus or minus the nth root, and that's jolly awkward. But at any rate, so now we've actually proved the binomial theorem, where the exponent is a rational number whose denominator is odd. Well, actually, we only proved it for a positive rational number, haven't we? But we can do the negative ones easily, because now, so if q is this positive rational number, then fx of minus q times fx of q is fx of 0, which we know is 1. And so fx of minus q is 1 over fx to the q, which is therefore 1 plus x to the minus q. So now we've proved the binomial theorem whenever the exponent is a positive or negative rational number whose denominator is odd. But now let's think about a real exponent. So these two things here are both continuous functions. That definitely is. And we established right at the beginning that that is too. So if they agree on all rational numbers with odd denominators, they agree everywhere. So they're equal for all. So we're done. But now I want to go back and think about what a real power, in particular an irrational power, really is. Because I'm not sure that that's really addressed terribly well in the A-level syllabus. So we learn what a rational power is. So we know that x to the 2/3, for example, is the cube root of x squared. But then the syllabus at least doesn't mention anything about defining what an irrational power is. But later on, we sort of magically work out, we work with the function e to the x, where x is any real number, but nobody's ever told anybody what an irrational power is. So let's look at that. So what is 2 to the pi? Well, it certainly isn't the product of pi copies of 2, is it? That's nonsense. So what is it? Well, we can work out roughly what value it ought to have, because we know how to approximate pi. And so we can work, and these are rational numbers, so we can work out those okay, and they're those, and those are obviously converging to something. So we sort of know what 2 to the pi ought to be. And it's a bit odd, isn't it, that this looks like an algebraic operation, but we're going to have to define it by taking limits. Well, I'm afraid we do. That's the way life is. It's rather awkward. Let's do this properly. So suppose we have we've got a real number and we've got a irrational r. Well, we can consider rationals either side of r, if you like, q just a bit smaller and r just a bit bigger. So we know what x to the q and x to the s is, and all these are less than all those, because this is an increasing function. But there's no biggest x to the q, because given any q less than r, you can find a bigger one. And similarly, there's no smallest x to the s. On the other hand, there can't be two numbers between all those and all those, because we can choose a q and s as close together as we like, And because this thing is continuous, we can make x to the q and x to the s as close together as we like. There's no room for two numbers between all the x to the q's and all to the x to the s. But there's no biggest and no smallest. And there's exactly one number between all the x to the q's and all the x to the s's. And that's our definition of x to the r. So that's sort of fundamentally and deeply different from the way we define rational powers. And that is very interesting. It's what makes the real number such an interesting and peculiar place, really, that we have this combination of basically algebra, multiplying and adding and stuff, and these limit things, and topology, if you like. So we can see where 2 to the pi actually is, and we can illustrate that last example here. So all these numbers are 2 to the something that's less than pi, and the blue ones are ones that are 2 to the something bigger than pi. So we got the decimal approximation. We've also got this one, which actually isn't a terribly good approximation, and this one, which is a super approximation. And there's just one number between all the red ones and the blue ones, and that's 2 to the pi. So going back to here, that's how we define it. But of course, it's all very well doing that, but it's got to work. So we need to check that when we've defined it that way, this sort of operation works. Because otherwise, it's not going to be a useful definition, is it? Well, it is, because we can choose a Q1 and an S1 either side of R1, and a Q2 and an S2 either side of R2. And so we then know that's equal to that, because those are rational, and that's equal to that. And these are all these are less than all those. And in just the same way, there isn't room in between these two things for more than one number. But this one is definitely between that one and that one. And this one's definitely between that one and that one. So they're both in this gap, but there's no room for the two of them. So they've got to be the same one. So yes, that is equal. So again, it's a sort of topological proof rather than algebraic proof. So anyway, I think that's all very interesting. So I hope you enjoyed the video.